All right, so if people don't object, somebody wanted to do selection sort. So is that person here? What I had done in class boils down to this page here, right? The loop invariant says that some are sorted and the rest are not sorted. And the way you maintain the loop invariant is to insert somebody. But they then complained that that wasn't formal. So and they said, well, how do you make it formal? And so that's the question here, is what we did with those pictures. You know, he's complaining it's not formal. I did this wavy, hand wavy picture here. Is that not formal? So there, you know, how do you write it up? So this is me saying, oh, for me, somewhat this picture with a little text to explain it is pretty good. But let's do it the way we did it before, right? We did we had that section of slides, which is you start with the loop invariant, and from the loop invariant you produce code. So let's just say what we're doing with sorting. So what's the precondition is that you have an array of numbers. The post condition is that those numbers are sorted. The loop invariant is that the first I are sorted and the rest are on the side somewhere. Everybody good so far?
Yes.
Right?
Yeah.
And like we did with the summing example, we didn't know what the code should be yet, because we're trying to design the code from the loop invariant, but we know our measure of progress is how many we've sorted. So we're going to increase that, right? And now our job is to prove that we can maintain the loop invariant. And as we prove it, we will design what we want our step to be, right? So we start by saying, what do you write on the test? You write this stuff, you write this stuff, you write this. This says that I and A sub t are the values at the top of the loop versus t plus 1 after you've gone around for a bit, right? Everybody good with that statement?
Mm-hmm.
Right? And then what do you want to write? You want to say from the loop invariant and not X in condition and the code of the loop, when you come back to the loop is true again, right? Everybody good with that?
Mm-hmm.
So then we just say, what is our loop invariant, right? And all I'm doing is copying down the loop invariant here, except I've added the t's because I'm saying the loop invariant is true at time t. And so those are the values of our variables at time t, right? And then we can copy down here the loop invariant at time t plus 1. So it's the exact same statement, except we got t plus 1s in it, right? And then we're not worrying about the exit condition yet, because we don't want to be worrying about it all at once. We're just assuming we're somewhere in the middle of the computation. But we took our partial step and converted it into math, right? And so now we want to link this up to this, and the first step is let's translate. Here we have t's and here we have t plus 1s, and that's no good. So we want to translate into the same notation. All right, so here this statement and this statement are exactly the same, except I replaced it plus 1 with it plus 1, which is what we got from this line here. The other difference I did is I wrote down the previous object here, right? And oh, here it's the same thing. Here the IT plus 1 got changed to an IT plus 1, and there was already a plus 1, so we got a plus 2. Everybody good with that?
I'm kind of confused. So the last one is for which part? The t plus 1?
Which last out down here?
Yeah, the last line, like the at plus 1 is going till I t plus 1, whereas the first one is like 1 is going till I of t, and then after that it plus 1. What is the, like, which one?
You got this line here. It's just the loop invariant at time t plus 1.
Yeah.
Right. So this line here is exactly the same with this translated in, right? So here,
Oh, so you just substituted that.
I just substituted this in.
Oh, okay, okay.
Right. And the reason I did that is because then we can compare these two things better, right? Because they're both in terms of the same I, right?
Yeah.
Then here I'm going to take the same statement here, and I don't really change it much. I just pulled out the next value, right? Here, the rest started with this I plus 1, and I brought I plus 1 out. Seems like a bigger I. I don't know why the font's different, but everybody see nothing really happened there, right? And then we want to say, well, what math do we need from the code, right? Do we need to get that this line gives me this line, right? You just compare these two lines and see what's the difference, right? And you know it's insertion sort. So here we want to translate this thing into this thing. And this thing says, I have I things sorted and I have an extra. And this says, well, the I plus 1 objects have been sorted. So how do you get from this line to this line? Well, you take this object and you insert it, right? Does that make sense? And then what about over here? Here's a T and here's an AT and an AT plus 1. What do we do to get from here to here? Absolutely nothing, right? So if I was writing this up, maybe I should have said this. If I was writing this up on a test, I would just say, what is my code B? My code B, I would write it in English. I insert this object into the list, and then we're done, right? Everybody good with that?
Yes.
Right. So I'm just saying it's, the reason I did it by proof by picture is because there just wasn't much to say, right? I felt I said all of this, right? Does that make sense?
Yes.
All right. So now, let's go on a roll. You shouldn't have to, on a test, you shouldn't have to do the inner loop as, you can just say things in English if you want. You could say in English, insert this, insert that value. But if we're on a roll here, let's now come up with the code for inserting, right? So what's the inserting problem, right? We want to get from this to this, and I'm just using a slightly different notation. Here's an array of A objects, and the precondition is that these A objects are sorted, and we have an extra object C, right? So that's the same as what we have here. We have not A objects, they're I objects, right? And here we have I objects, and we have an extra value, which I'm calling C, right? And then what is our post condition? Most post condition is it's the same objects, right? The A's are the same. I've just taken the C and I've put it somewhere, right? And it needs to be sorted. And so that's what we're doing, going from here to here. Everybody buy that?
Mm-hmm.
right? So now we need a precondition, we need a loop invariant. Any guess what we would have as a loop invariant? Right? So our loop invariant is what? Right? We're taking the C and we're going along the list, either forward or backwards. And I guess I'm going to be going. And what we're saying is, our loop invariant is that we've inserted it somewhere, right? Here's our A, and we want to insert it in the right place. And now I'm claiming that this isn't necessarily the right place, even though I use the same indexes. This isn't necessarily the right place, but the loop invariant is like inserted the C somewhere. And then we're going to need some more requirements. What are the requirements on the A's? Is that the A's are still sorted, right? It's still the same A's, still sorted. And we need some statement about the value of C. Anybody, I guess what we need for C?
Like compare it with other A's?
Yeah, exactly. And if we're moving the C backwards, right? The C started off here and we're moving it backwards. The A's we've compared it with are the A's that are farther along. We haven't looked at these A's yet, right? So we can just add in the extra statement that this part is sorted, right? Because C is less than AJ and then the rest is sorted, right? Does that make sense?
Mm-hmm.
Right? So that's just my loop invariant that I've inserted C somewhere and we know C is less than everybody after it, right? And our partial step is we're making progress by having J smaller, right? So J is getting smaller, C is moving to the left. So now we have to maintain the loop invariant exactly the way we did before, right? So what's our loop invariant? Well, we copy it in. This is a direct copy. Everybody understand the loop invariant? Right? And here I'm just copying down the loop invariant for the next time step. Now here I'm cheating a little bit. I didn't do the J at the top of the loop versus JT versus JT plus 1. Here I just copied in it with the exact same value of J. And here it's the same. I'm claiming this is the same loop invariant, except here C is before AJ and after AJ minus 1, and now C is before J minus 1 and after, right? So it's been shifted, right? What's the difference between what I have here and here is I included the previous one, right? I just named the previous one. And why did I name the previous one? Is so that we, right? Can everybody, oh, and then here, what's the loop invariant is that C is less than the guy after it. And so, right, here C is less than the guy after it. So here I have C is less than the guy after it. And here I have C is less than the guy after it. Right? Everybody buy that?
Mm-hmm.
Right? Well, now we know what code do we have to get from this to this. Right? Well, you can see it's mainly we swap those things. Right?
Mm-hmm.
Here we just swap the order of those. C is bubbling down. Now, what about this statement here? Right? Oops, the answer came out. How do I know that C is less than this guy before it? We haven't checked that yet. Right? So maybe in our code, we could check that. But one way to check it is to check it in the exit condition, right? I know that I'm not exiting. Why am I not exiting? Because C is less than this guy. So I need to swap further. That's why I'm not exiting. So I'm gonna have this condition as my exit condition, right? And now everybody buy that this loop invariant plus this not exit condition gives me the loop invariant again, right? Does that make sense? Am I with you guys? Somebody wanted me to do this. Or I don't know if you
Yeah,
guys, the person
we are
who wanted to
here.
do it, right?
Yeah, we're
Everybody's
here.
good with,
That makes sense.
yeah? Right, and so here I'm adding my, what's my exit condition now? Well, not exit is this statement. So the negation of that is this statement, right? That's my exit condition. Right?
Mhm.
Now we have to figure out how to establish the loop invariant. So we want to know from the precondition in the code at the beginning, how do you get the loop invariant? Well, let's just copy down the precondition, right? That's the precondition, copy down. Copy down. Now we want to say, what should the loop, we need to get the loop invariant true, right? So we want to copy down this statement, but we want to do minimal work. We want it to look as much like the precondition, right? So where should the C go at the beginning? Right? It's just going to go there. We're going to put it, the C is probably sitting there already, right? So we don't have to do anything, right? We just put the C there, right? And now what do we need for the loop invariant? We need C's less than what? Well, C has to be less than the A that's before it. Sorry, the A that's after it, right? In our loop invariant, oh, here's our loop invariant. C's less than the A that's after it, but we don't have any A's after it, right? So we just don't really have to worry about this condition. All right, everybody buy that? And that establishes the loop invariant. Right? I guess what we do need is we need to put the C on the end if it's not already there. And what's our initial value of J? Well, here I guess J minus 1 is the number that's before C. And here the number before C is I. So we need that relationship. Right? Everybody good with
So
that?
J is incrementing in this case?
J, this is establishing the loop invariant. So we're at the precondition, we have no value J. Right?
Oh, okay.
Right? And so the code at the beginning of the loop is giving our initial value of J, which is C's here at, right? We're taking here our precondition and we're just putting C here at the end. And that makes it look like the loop invariant, C somewhere. Where is C? Well, C just happens to be at the end. So for the loop, right? So then who's before the C here is J minus 1. Who's before the C here is I. So what's the value of J, right? Does that make sense?
Mm-hmm.
Now we got to get the post condition. How do you get the post condition? Well, we have the loop invariant plus the exit. We know the exit's true because we're exiting, and we do a little bit of code at the end, and we have to get the post condition. So we copy in here the loop invariant, right? That's just the loop invariant directly copied. We copy in the exit condition, right? We know the exit condition is true because we're exiting. And what do we want to get? We want to get the post condition. And what's the post condition? It's written up here, is that's just copied down, that's sorted, right? Everybody buy that?
Mm-hmm.
Oh, I have a question. So
Yeah.
for the exit condition, do we need to add one more? Like J should be greater than 0?
I suppose you might want to make sure that you're not falling off the edge, but let's just assume that we have an A0 that's negative infinity, so we don't have to worry about it. But yeah, you're right. We probably should be checking that too.
Okay.
Right. So now what do we want to do? We want to prove this. We want to prove that this is sorted. And so in order to prove it sorted, we have to prove that each consecutive object is sorted. right? So how do we know that these guys are in the right order? How do we know the A's are in the right order?
If aj minus 1 is less than c and c, no, I mean, yeah. And
Yeah, you
then
get,
aj is greater than c.
yeah, you're getting too far away, too far along. I'm just saying, we know that the A's are sorted. We
Oh,
know from that the A's are sorted, right? How do we know that those are in the right order? Is because we have it
By
there.
checking exit condition.
Yeah, the exit condition. How do we know those are in the right order? Because that's part of our loop invariant, right? And so what do we have to do in their code? Absolutely nothing. We get the post condition. Does that make sense? So was that
And-
useful?
And
Make it up.
yeah, that was useful. Also, one more thing, like, you know how we got from the inner loops loop invariant to post condition?
Yep.
Do we need to tie in the outer loops loop invariant to the post condition?
Oh, so the big picture here is we're doing the code for insertion sort, for inserting, right? The post condition that we're tying in is not the post condition of the loop of the sorting. It's the post condition, right? So the second thing we were doing, let's review what we were doing here, right? So here, when we're doing the insertion sort, right, we're saying, what does code be inside of this is the outer loop where we're, oh, no, sorry, wrong, back. Here we are, right? This loop is the loop of the outer loop of the sorting algorithm, right?
Yeah.
And on a test, you have to say, how do I get from this loop invariant to this loop invariant? And since it's a test about sorting, you don't need to give lots of details about the inner loop. So it's okay to just say, oh, what's my code B? My code B is that I take some object from the rest and I insert it. Right? So
and then from like the final loop invariant and an exit condition, how do we like say like the post condition? We just say like directly that since the loop invariant at t plus 1 is true, and then the exit condition. Oh, what do we have for exit condition in this case? Because we need to have like exit condition true first.
I didn't complete this code because why didn't I complete this code? Is because you come back. Let's see. Let's take this slide here. Right? I mean, how do you establish the loop invariant? You just say nothing is sorted. How do you get the post condition? The post condition is that everything is sorted. You just say when I equals n, we're done.
Okay.
Right? So I didn't bother write those ones up again. I thought it was pretty straightforward, so I didn't bother, and it was getting late. I went to bed. But and I also wanted to flow from, right? So here, I guess we can.
Professor, we see your desktop now, like the picture of.
Yeah, it's sort of funny that way. If I'm not displaying something, then you don't get to see it. Anyway, do you have any other questions about this example? Did you see how we did the proof for the outer loop, and then separately we did it, and we used the inner loop as a subroutine? Right? here I'm just saying the outer loop has its inner loop just as a single statement you insert,
Mhm.
right? And then we go on and prove the inserting one separate.
Okay.
Professor,
Yeah.
just a quick question regarding the C, where we were trying to prove that the C is really greater than the AI value. So what does that really implicate?
So C is greater than what? C is greater than A.
AI. There was a slide where we put the C at very front. Maybe go next slide.
Where we're starting this guy here.
Yeah, this one. Yeah.
Yeah, so we need to establish the loop invariant. So we have the precondition, and I'm saying the way to establish the loop invariant is just take the C and put it at the end of the list, where actually it probably is already, right?
Mhm.
And then we need this condition. Well, what's this condition say for the loop invariant? It says if C has been moved past something, then it needs to be less than or equal to it, right?
Right.
And here, right, so what has C been moved past? Well, C hasn't been moved past anything. So it's automatic that C is less than everybody that it's been past.
Okay. So
Right,
just
does
to
that make sense?
establish a precondition and create the next step for the loop invariant, we are just showing that C really in front of AI has nothing, as in we are not including it. That's what we really meant here.
Yeah, I guess here the loop invariant says that we haven't yet compared to C to the A's that are before it, right? And so here C is at the end. So yeah, we haven't compared it to the A's that are before it. So we're good to go,
Okay, thank you.
right?
Mhm. And I'm kind of confused because the loop invariant here seems to be the same as the post condition. But then in one of the slides, you said that loop invariant is not the post condition.
Yeah, so they're not the same, right? The post condition says that you've inserted the C somewhere so that the entire list is sorted. What's the loop invariant? You've inserted the C somewhere. Now, we don't know the whole thing is sorted. What do we know? We know that the A's are sorted, and we know that the C is less than everybody it's been moved past, right? We don't know, C could be bigger or it could be smaller than this next A, right? If it's,
Okay.
right, if C is bigger than the next A, then we will exit and we will get the post condition.
I'm sorry. So could you please say that again? So if C is bigger than what?
Right, so here we say we're at the top of the loop. Let's go. Sorry, I keep meaning to close it. My neighbor, my housemates say I'm too loud. All right, so here, what do we have? We're at the top of the loop, and we have this statement, right? We know that the C is less than the A's that are after it, but we haven't compared the C's to these guys here. So what do? We have our exit condition, checks. Hey, it compares C to this number, to this AJ minus 1. And if C is bigger than that, if C is bigger than this, then they're sorted, right? So we exit.
Okay, I see.
And if C is smaller than this number, right, then we swap, right? And how do we get this loop, right? When we swap them, now C has to be less than that number, right? And how do we get that? We get it from our not, because we didn't exit.
And what if the C was actually smaller than J minus 2, but then our exit condition is a J minus 1?
Oh, now So we've gotten that if C is less than the AJ minus 1, then we swap them. And we still haven't worried about this A yet. That's for the next iteration. Right? We just have to get the loop invariant right. The next iteration, C will be compared to this one.
Oh, okay.
Right? We're only doing one step.
Okay. And one more thing, you know how we said that the right side would be like unsorted variables, like numbers, like elements, and then the left side is the one that's sorted. But
Yeah.
then here we are only inserting like 1C. So would
Yeah.
it be like we should say something like CI? So then, you know, there are like numerous C's that needs to be inserted.
So I think you're mixing up the two steps.
Oh.
See, there's an outer loop. Maybe I should add here what the final code is, right? The outer loop job is to take the loop invariant for the outer loop is that some are sorted and the rest are on the side, right? And for the outer loop, how do we maintain the loop invariant? You take this next number and you insert it, right? So this page here tells you how to maintain the outer loop. Now, what is the inner loop? The inner loop is this inserting. And how do we do the inserting? Well, there's an inner, we have to go from here to here, right? So how do you do the inserting is we have to go from here to here. And so that's what this precondition is saying that we're here. And the postcondition, this is the postcondition of the inner loop, right? This is the inner loop. So that's the postcondition of the inner loop.
Okay.
Right here, we're just doing we're doing the inner loop.
All right.
Right? And this gives us the loop invariant of the inner loop. Right? Does that make sense?
Yeah. Can we go back to the sorting one once again? Yeah, no, the code from the LI part for sorting, yeah. How did we prove the loop invariant from precondition for this one?
All right.
Because
So
like, when we were trying to do this, we were a bit confused because, like, you know, in precondition we only had like A1 to N, but then the loop invariant had two things in it.
all right. So I didn't make those slides, but suppose the precondition is true.
Yeah.
Then how do we establish this loop invariant? All you have to do is set I equals 0, right? All the initial code will set I equals to 0. And then what does the loop invariant say? Well, this becomes the empty list, right? It says the empty list is sorted, and it says everybody else is the rest, right? This, if I is 0, then this is 1 through N. So we're done.
Oh, okay.
Right? Does that make sense?
Yeah.
And now how do you get from the loop invariant and the exit condition, how do you get the post condition? Well, you exit when I equals N.
Yeah.
Right? When I equals N, this 1 to N tells us that it's sorted. And this rest is nothing.
Oh, right.
Right? So somewhere I was trying to grab that picture, but maybe I didn't actually drop it. I was going to drop it and maybe it didn't go. Let's see. No, I didn't. So I was trying to, this is how I did it with the pictures, right? The precondition is that everybody is on the precondition is you have a bunch of numbers unsorted. And how do you establish the loop invariant? You say, well, the empty list is sorted,
Mm-hmm.
right? And everybody else is on the side. And then the exit condition is when you've sorted them all, right? In which case, all you have to do is get rid of that, right? And you're sorted.
And I
That's
have
the-
one more question.
Uh-huh.
You know how you use like the box and the bubble thing to represent left and right side? So are you doing insertion sort in place, or are you using like two different arrays here?
It's all in place.
It's all in place. Okay.
Yeah. Yeah, I can show you that it's in place.
So basically they're like left side is null and right side is null. That's like a conceptual thing, not a physical thing.
Here, oh, in the picture, I was conceptual, but here I'm very concrete. It tells me that the numbers that I have one array, and then the numbers that are in from 1 to I are sorted, and the numbers that are in I plus 1 to n are the rest. So I'm telling you, right here, I'm always using A. So there's only one list, A. Now, why is there an AT versus T plus 1? It's the same array. It's just AT are the values in the array at the top of the loop versus after you've gone around the loop.
Mm-hmm. Okay, okay.
Right?
Yeah.
It's all in place in one array.
Okay. Thank you so much.
Yeah. All right. Well, anyway, any questions about this example?
Sorry, one quick question relating to the inserting part. So for the C and A J minus 1, if C, like I saw you saying writing swapping in English.
Yeah.
So in the whole process, we just write swap if AJ minus 1 is greater or equal to C, like before the exit condition, right?
Yeah, so I hadn't said the exit condition yet. I mean, what the point is, you're just saying, I fly in from Mars, I know this is the picture, right?
Yeah.
When I go around the loop, what do I need? I need this to be the picture. So
Yeah.
how do I get from this picture to this picture? Well, you just compare the pictures, and the one obvious difference is that I swap.
Yes, but there, like the swap process need to place before before code B or after code B.
It is code B.
Okay, so it should be inside code B. Okay, thank you.
Yeah.
Okay.
Should we, is it worth writing out the code for this? Or are you people get it?
Didn't you already write it out on a slide?
Yeah, you're right. It is written somewhere, isn't it?
Yeah, the double for loop, right? Like, so I guess I have a follow-up question to this whole ordeal we just did with, I remember earlier in the course you said that if that inner loop is not the focus of the algorithm, I guess, right?
Yeah.
Then we don't really need to define a loop invariant for it.
Exactly.
This was kind of just to be extra, right? What we
That was
just
an extra.
did.
That's what I kept trying to
Okay.
say. And
Okay.
maybe I should put it in the slide, is that you only needed to do the outer loop, right? The inner
Mhm.
loop, where's my, here, the inner loop, you would just say, right?
it
I
in
mean,
the
there's
right
an
place.
outer loop what does the outer loop do? It moves the I along and it inserts, right? And now how do you do the insertion? Is all you do is you do a,
swap it from the end all the way to into your list up to
Yeah.
I.
Oh, I see. I'm not
Yeah.
swapping it. The last guy is held up somewhere. Here I'm holding it in B, right? So this
Yeah,
B is my value C. And
you're
so
swapping,
I
right?
don't put the C in place. I'm just shifting them along.
Yeah. Okay, I see.
And
Right,
I
does
have
that make
one
sense?
question.
Yeah.
So you know how in the while loop you're actually doing the comparison, like AJ minus 1 is greater than B. So isn't that part the one that's actually doing the sorting part, because that's the one that's doing the comparison?
Yeah. Well, the insertion, we're inserting here. This is says, have we put B where we want to put it yet? And if the answer is no, then we shift we move the A along.
Because to me it kind of feels like we're like sorting and inserting in the while loop, because in the while loop condition we are actually comparing like the previous value with the value B.
You want me to rewrite this code so it looks more like what we're doing in the notes in the slides?
Sure, but if it's not too much trouble.
Well, we got this time. You guys decide what
Okay.
you want to do with the time.
Okay.
All right. So if I was really thinking that this example was going to bore everybody, but I guess you're not bored with it. So all right. So what do we want to do here? Oh, I should move this. Oh, let's see. Move this to the screen that we are doing. There. Can you see that? Now you can see it, right?
Mm-hmm.
I'm not very good at editing in real time. I could do it offline and come back to you.
Yeah, you can do it offline if you want.
Yeah, whichever you want.
Yeah, it's fine if you want to do that. And then let us know once you upload the recent version, like after
Yeah.
you made the edits.
Yeah. What do you guys want to do now? I can either edit this online or we can go to a different example.
Can we do something else? I feel
Yeah,
like we've done
that's-
insertion sorts so many times.
I know, exactly. I was like, that's what I was like, not wanting to do it at all. All right, what do you want to do now? You see